let's suppose that we have an ellipse, this particular ellipse here, and we want to figure out what is the biggest rectangle that we can put inside this ellipse so that each vertex of the rectangle is touching the ellipse the way I have it here. Well, let's think about the problem now. In other words, we're thinking of, let's see if we can get a model for this. So what I've got here is, if you think about this little rectangle right here, where I've got x and y, of course the area of that rectangle is xy. Now we don't want just that rectangle, we want the whole thing. So that's 1, 2, 3, 4. There are 4 of those. So we've got this is a model for our area. So as let's let K be the actual area. So what we're saying is 4xy equals K, and what we're trying to do is we're trying to find out, well, how big can K possibly be with the constraints of being inside this ellipse. So now, of course, this right here, this 4xy equals K, that's a hyperbola. You know, you could write it this way. You could say that's 4 over x, and then you can clearly see, yeah, that's going to behave like, that's a hyperbola. Now, if you graph the ellipse and this hyperbola together, you see what it looks like in these 2 graphs, right? These 2 graphs right here. Now, let's suppose, so here's the hyperbola right here. Here's the hyperbola. Here is the ellipse, and this purple is a rectangle that we could put inside that ellipse right here. This represents a rectangle with the area of 6. And notice its vertex here is at the corner, is at the intersection of the ellipse and the hyperbola. And then it goes down, and you see you've got an area of 6. Now, if we make the rectangle a little bit wider, we've got the area equals 10. And you can see we're looking right here. The corner of the rectangle is right here at the intersection of the hyperbola and the ellipse. Now, think about this. Think about the tangent of the hyperbola and the tangent of the ellipse at both of these intersections. And you can see that they're not alike. They're certainly not parallel. You know, they don't have the same steepness. But if you look at the tangents for the rectangle with area equals 6 versus the one with area equals 10, you can see that they might be a little more alike. So let's notice this. As we move to the right, the rectangle area gets bigger, and the tangents get closer and closer to being parallel. Let's look at that. Okay, so here is the situation when the area is 2. Here's the situation when the area is 3. So think about the tangents. Think about the tangent of the ellipse, and think about the tangent of the hyperbola as I move to the right. So when the area is 8, here's where the intersection. 9, 10, and so forth. Now, I could keep going. And you notice that at some point, though, so the area increases. The area increases as we move to the right. Okay? So it keeps increasing. The tangents get more and more alike. But at some point, the area keeps increasing, but we're outside our constraint. See, there's no longer an intersection with the ellipse and the hyperbola. So we have to move it back. We have to go back until we're right there at the intersection. Maybe there. I'm just eyeballing it. But here, notice we've got an area of 16, and it looks like the tangent of the ellipse and the tangent of the hyperbola are the same. That's what it looks like. And in fact, if the tangent vectors are parallel, then the normal vectors must also be parallel. So that gives us some insight into how we're going to use what's called Lagrange multipliers. Let me rewrite this objective equation right here as a level curve. So I'm going to call this f of xy equals 4xy. Of course, that equals k. And let me name the constraint g of xy. So we've got x squared over 4 plus y squared over 16 minus 1. So I'll just have these two level curves, and I'm writing them as level curves because now I can calculate the gradient. Okay, so let's do that now. So here goes the gradient. I've got the gradient of f, and that equals, let's see here, we've got 4y and then 4x. Okay, that's the gradient of f. And now let's get the gradient of g. Okay, so I've got, let's see here, the gradient of g, I've got 1/2 x, and then for the partial with respect to y, I've got 1/8 y. Yeah, there are my two gradients. Okay, now here's what I want. I want to find where these two gradients are parallel to each other. In other words, what I want to do is I want to find out where this happens. Remember, parallel lines, if you have two vectors that are parallel, then that means they're multiples of each other, they're constant multiples. So I'm going to find the place where this gradient of f, and I'm going to use lambda as my constant, my constant is equal to 4y, 4x. So I'm going to use this relationship here along with some algebra to see if I can find out where is the point at which you have the tangent vectors are equal, or the tangent vectors have the same slope. And I'm going to do that by finding where the normal vectors are parallel. So here I go. So here's the way we proceed. We've got 4y, 4x equals lambda 1/2 x, 1/8 y. Okay? Now, I've got some algebra to do. So this all boils down to a lot of algebra now. So look what we've got. We've got 4y equals 1/2 lambda x. So I'm just equating the parts. 1/8 lambda y. And then let me put my constraint down here. So I'll always have it in the mix. X squared over 4 plus y squared over 16 equals 1. Now, it's all about, from this point on, it's all about the algebra. Okay, so here I go. There are different approaches. A lot of these problems, they cause you to have to use different algebra tricks. What I'm going to do on this one, and this is what you can do in a lot of these, is just solve both of these. And let me call this equation 1, this equation 2, and this equation 3. Let me just solve equation 1 and 2 for lambda. Now, if I do that, I get, from this first equation, I get that lambda is equal to 8y over x. And in the second one, I get that lambda is equal to 32x over y. So I get these two things. Now, since I've both of these are in terms of lambda, I can just equate them. So here's what I do. I say 8y over x equals 32x over y. And maybe I should multiply both sides by xy. Or you could think of it as cross-multiplying. But here's what I'm going to get. I'm going to get 8y squared equals 32x squared. And if I divide by 8, I get that y squared is equal to 4x squared. Now, here's what I can do with this. I'm at the point now where I can go back to my constraint. Remember, my constraint was x squared over 4 plus y squared over 16 equals 1. I know what y squared equals. I can replace any place I have y squared, I can put 4x squared. So let's see what I've got then. I've got x squared over 4 plus 4x squared over 16 equals 1. And all I did was replace y squared with what it equals, and that's 4x squared. Now, I've got this thing. I think what I want to do is just multiply through by 16 to clear out the denominators here. So I've got 4x squared plus 4x squared equals 16. Just multiplying through by 16. And let's see what this gives us. This gives us 8x squared equals 16, or x squared equals 2. And let's just say, and so solving this, I'll get x equals the square root of 2. Now, I'm not going to put plus or minus the square root of 2. I'm just looking for, remember the way I drew this initially. This is x right here. It's positive. So I'm just interested in that length. I don't need to put plus or minus the square root of 2. Okay, so there's what I got now. Whoops. Okay, so I've got that x equals the square root of 2. Now, we also said this. We said that y squared is equal to 4x squared. That's what we had. That's what we found out earlier. So if that's the case, let me just replace x squared with square root of, or let me replace x with the square root of 2. And we got that y squared is equal to 4 times the square root of 2 squared, which gives me that y squared is equal to 8. Or y equals the square root of 8, 2 square roots of 2, another way to say it. So now we have x and we have y. So let's see what our area would be then. So this is what we have. We want to find f of the square root of 2, comma, 2 square roots of 2. And I want to see if I can figure out what the area is going to be. So this is 4x times y. Whoops, I put an x there. That's x is the square root of 2. Okay? So let's see what we've got here. We've got 8 times, so this is 8, and then square root of 2 times square root of 2 is 2, so we got 16. And this is the optimal area. And that happens whenever x is the square root of 2 and y is 2 square roots of 2. Okay, now let's look at another example. We want to optimize this with this constraint. Okay, so I've got f of x, y, z already defined. Now I'm going to call this one g of x, y, z. This is my constraint. So what I want to do is I want to take the gradient of f, which is 1, 1, 1, and set that equal to lambda times the gradient of g, which is 2x, 2y, 2z. Then I just pour some algebra on it, right? In other words, I want to say, okay, I've got 1 equals 2 lambda x, 1 equals 2 lambda y, and 1 equals 2 lambda z. And, of course, my constraint, x squared plus y squared plus z squared equals 25. There. Now, so every time you get to this point, you're thinking, okay, what kind of algebra technique am I going to have to implement here? What kind of, how am I going to approach this? So sometimes you have to be creative. This time, you don't have to be real creative because one of the things you note is that x and y and z are all equal because 2 times lambda of x, 2 times lambda y, 2 times lambda z, they all equal 1. So that means that x equals y equals z. So let me just go from there and say, okay, well, let's just take that down to this constraint. So here's what I have. X squared plus y squared, well, y and x are the same. Plus z squared, well, that's the same. Okay. So what we have now is we have 3x squared equals 25. And that means that x squared equals 25 over 3. Which means that x is equal to plus or minus 5 over the square root of 3. There, that was pretty easy. So there wasn't a lot involved in that. We got right to what we were looking for. Okay, now, so we're past the hard part. Now, what I want to do is I've got these numbers. I've got 5 over the square root of 3, and I've got negative 5 over the square root of 3. So let's just do some computations here. We've got 5 over the square root of 3, 5 over the square root of 3, and 5 over the square root of 3. So plugging those back into the f function, we get, let's see here, I computed this a little bit earlier, 5 over the square root of 3. So that's just putting it back into the function. And I did the computations earlier to save time on the video. Then we go through and we say, okay, what about this? Negative 5 over the square root of 3, negative 5 over the square root of 3, and negative 5 over the square root of 3. Well, if we do that one, we get negative 5 square roots of 3. And so if you look at these two, what you get is you get up here a local max, and on this one, a local min. Okay? So that's an example of how we approach these problems using Lagrange multipliers from the beginning. Okay, so let's look at another one here. Now, what I'd like for you to do is pause the video and try to work through this one. Now, you can do that if you want. I'm just going to go through here and work it, but if you want to kind of test yourself to see where you stand, you can do that. But what we would do is, okay, so I'm going to set the gradients equal to each other. So here's what I've got. I've got 2x, whoops. Okay, so here we go. I've got 2x equals lambda. I've got 2y equals lambda. Okay, 2z equals lambda. And then I've got the constraint, x plus y plus z equals 25. And once again, like the other video, you find that, well, x, y, and z, they all equal the same thing. So what I've got now is I've got 3x equals 25, or x equals 25 thirds. So it's very much like that other one. And then we can go ahead and plug in to actually find that if we plug this in, we find that that's equal to 625 over 3. And that's actually a local minimum. I don't want to focus on is it a min or a max right now. We want to get the techniques down. But anyway, there is that. Now, let's look at another. Now, this example will require a little more algebra. It's a little bit trickier, but still we approach it the same way. So I have my function here, and I want to look at the partial with respect to x. Well, my partial with respect to x is going to be negative 4y plus 8x. Okay, that's the partial with respect to x. And I'm going to set that equal to the partial with respect to x times lambda of my constraint. So this is 2x lambda. Now I want my partial with respect to y, and that's going to be 2y minus 4x. Okay, 2y minus 4x. And that equals the partial with respect to y from my constraint. So that's 2y lambda. And then, of course, I've got the constraint, which I put here. Okay, there's my constraint. Now, so in this one, the algebra is a little more involved, of course, than the others. But one thing I notice that I could eliminate one of these variables up here. For example, let's suppose that I multiply, and let me call this equation 1, equation 2, and equation 3. Okay? So let me just think about the elimination method here. I'm going to take equation 2 and multiply by 2. Because look, that would get rid of the y's. It'd also get rid of the x's. You might think, well, we don't want to do that. But let's see what happens. We got negative 4y plus 8x equals 2x lambda. Now, if I multiply equation 2 by 2, I get 4y minus 8x equals, now remember I'm multiplying by 2, so I'll get 4y lambda. Now, let's see what we're left with here. On this side we got 0, and on this side over here, it looks like we've got 2x lambda plus 4y lambda. Okay, well, now we've got one side equaling 0, so let's just use the zero product property. Let me factor out a lambda. And I've got 2x plus 4y. Now, this right here gives me a couple of options. This equation gives me this option. Lambda could equal 0, or 2x plus 4y could equal 0. If either one of these things happens, then I have my solution. So lambda equals 0, or x equals negative 2y. Yeah, either one of these. Either one of these will work. So what we want to do is we want to go back and see, okay, let's see what happens if, let's say, lambda equals 0. So let's suppose lambda equals 0, and then we'll come back and say, okay, well, what do the numbers look like when x equals negative 2y? So if lambda equals 0, let's see how this plays out. If lambda equals 0, then what we have is, going back to equation 1 here, we've got negative 4y plus 8x equals 0. Now, if we do that, that implies that y is equal to 2x. Okay, well, let's see what that means, though. Now we've got y equals 2x, so let's go back to our constraint and see what kind of numbers we get. Okay, so we can plug in now. So in place of y, I'm going to put 2x. So we've got x squared plus 2x squared equals 1. That means that x squared plus 4x squared equals 1. And that means that 5x squared equals 1. And that, of course, means that x is equal to plus or minus 1 over the square root of 5. Now, if that's what x equals, and we know that y equals 2x, then y equals 2 times that, so plus or minus 2 over the square root of 5. Yeah, so there we go. So we have a point here, and now what we can do with that is we can say, okay, well, let's try these out. Let's suppose that I want to find f of 1 over the square root of 5, comma, 2 over the square root of 5. Okay, so that's our point when I put 1 over the square root of 5 with 2 times that. And then we could say, okay, well, let's also calculate the other point. So in other words, I've got 2 points here to calculate so far. negative 1 over the square root of 5, and negative 2 over the square root of 5. And now, if I do that for this first one, what I get is 0. And if I do that if I calculate this for the second one, I get a 0. So those 2 points that we got give us a 0. Okay, now, so let's see what happens. So we went down the path of lambda equals 0. Now let's go down the path of what happens if we say x equals negative 2y. So here we go. If x equals negative 2y, let's see what that gives us. Well, we've got x squared plus y squared equals 1. And if x equals negative 2y, then we've got negative 2y squared plus y squared equals 1. And that means that we've got 5y squared equals 1, or y equals plus or minus 1 over the square root of 5. Okay, now, that being the case, we've now got 2 points, putting that together. So x equals negative 2y. So here's what we've got. We've got 2 points that we're going to plug in. We've got 1 over the square root of 5, comma, let's see here, and we've got negative 2. So this is going to be actually, let me, I was looking at the wrong thing. We've got y is 1 over the square root of 5, right? Y is 1 over the square root of 5. And then x is going to be negative 2 over the square root of 5. And if we plug that into our formula, we get 5. Then we go back and say, okay, well, let's try the other one. If y is negative 1 over the square root of 5, then x is 2 over the square root of 5. And that also gives us 5. So I think we're about done with this problem. What we found is that we have 0 is a local min, and 5 is a local max. Local max. Now, notice what we did here. We just used one of our tricks, our algebraic tricks. We used elimination. We went up here and I multiplied equation 2 by 2 and added the 2 equations, 1 and 2, and we used elimination. Different problems call for different techniques. Maybe we'll have a situation like this and we'll use substitution. The bottom line is you're trying to get to the point where you have something like this. You have y and x presented in such a way that we can put those in to the constraint and actually solve for one of the variables. Either I can plug in like if I have y equals 2x, I can replace y with 2x, and now I just have an equation in terms of x alone. What we're trying to do is use our algebra to find a number, an x, a number, a y, a number, and then plug those into the function f of xy and actually see, do we have, what is the output? That's what we're trying to do with Lagrange multipliers.